How do we decompose an abstract vector into independent right-angled parts? To do this, we need a specific mathematical environment, a Hilbert space. Named after David Hilbert, this is a complete inner product space. It gives us geometric tools like length and angles, and crucial for our purposes, it has no missing limits or mathematical holes. Look at this standard 3D coordinate system. Think of this cyan plane as a subspace, which we will call y. Floating in the space above it is our distinct yellow vector x. If we want to approximate x using only the vectors available in subspace y, we drop a line straight down to the plane. This creates a new shadow vector, y, lying flat on the plane, and a vertical error vector, z, bridging the gap back up to x. Minimizing the distance between x and the plane requires that our error vector z is perfectly perpendicular to that plane. This is the logic of the best approximation. It is strictly orthogonal to every single vector inside subspace y. Orthogonality is the geometry of the shortest path. By ensuring our error is perpendicular to the entire subspace, we guarantee that no other vector in that space could provide a better fit. Normally, you can add two vectors together in many ways to get a sum, but if we represent a space as a direct sum, denoted by this circled plus symbol, every vector in the space has exactly one unique combination of parts. To achieve that unique split, we need the orthogonal complement, y perp. This magenta line represents y perp. A vector belongs to this set only if it forms a 90-degree angle with every conceivable vector on the cyan plane. Because these sets are perpendicular, they act as annihilators to each other. Take any cyan vector and any magenta vector, and their inner product is mathematically forced to zero. The projection theorem formally states that if y is a closed subspace, the entire Hilbert space can be written as the direct sum of y and its orthogonal complement, y perp. Notice the requirement that the subspace must be closed. If the plane is missing its boundary points, our dropped shadow might not actually hit a valid vector. It slips into that void and the decomposition fails. Let's think about the geometry. If you take the orthogonal complement of the magenta line itself, what do you get? You get everything perpendicular to the line. You reconstruct the original cyan plane y. The projection theorem guarantees that any Hilbert space can be perfectly fractured into a manageable subspace and its exact orthogonal complement. These rules apply even to abstract structures, like the space of continuous functions. Look at this asymmetrical curve on the graph. In this space, the entire squiggle is treated as a single vector. Using the direct sum, we can fracture it into two independent pieces. We get one function symmetrical across the y-axis, the even part, and one rotationally symmetrical around the origin, the odd part. These two functions are orthogonal because their inner product, the integral of their product, cancels out to zero. The positive and negative areas perfectly balance. Even though we are looking at abstract curves, the underlying math is identical to dropping a line to a flat plane. Function space geometry obeys the exact same algebraic rules as physical 3D space. This summary grid distills the framework into its core rules. First, the definition of the orthogonal complement. Second, the uniqueness of the direct sum. Third, the projection theorem itself. And finally, the rule that a set span is dense if its orthogonal complement contains only the zero vector. Grasping these complements allows us to isolate parts of a vector into independent subspaces. Even in an infinite dimensional space, we can now analyze a specific component without the rest of the vector interfering. If this visual breakdown helped you understand Hilbert spaces, please like, subscribe, and share this video. Leave a comment below with the advanced textbooks, like Kreyszig or Rudin, you want to see explained next.